Okay, so good morning everybody, and thank you for joining me today. Or good morning if you're in the UK. Good afternoon if you're pretty much anywhere else. My name is Doug Oldfield. I'm one of the business development managers here at Palisade Corporation, and what I'm going to be presenting on today is an introduction to risk and decision analysis using at risk. So the agenda really for today's session. I'm going to give a little bit of an overview about Palisade for those of you who kind of don't really know much about us, just so you know a little bit more about the type of organisation we are and some of the customers that we're dealing with, etc. And then I'm going to talk a little bit as a kind of introduction to this whole idea of Monte Carlo simulation, probabilistic analysis, quantitative risk analysis, whatever you want to call it, and also kind of introducing that risk at the same time. Now, I do a lot of these presentations, and it occurred to me a little while ago that maybe I don't talk enough about the whole kind of idea of the theory of this probabilistic analysis as a starting point, because I know that lots of you will already use the software. I seem to get quite regular people kind of signing into these sessions who obviously know how the software works and maybe just want to find out little tips and techniques, etc. But I'm also aware that many people on this call, and I think there's about 150, 160 sign-ups in total, will never have used at risk, may not have any idea about what Monte Carlo simulation is. So I just want to spend a little bit longer than usual this morning, just really kind of talking a little bit more about that. And actually, for those of you who do kind of watch a lot, after the session, I'd appreciate feedback to see what you think, whether it worked or not for you. And then after that, we'll obviously go into looking at the software, where I'll run through some different models and show how the software works in practice. So main goals, two main goals really. The first is really to provide an entry-level introduction into the world of probabilistic analysis. So if you've been doing probabilistic analysis for the last 20 years, some of today's session might be a little bit basic, but really the whole purpose is to hopefully show how probabilistic analysis can help to make better decisions. So we'll start off talking a little bit about Palisade. This is our 30th year this year, which is obviously a fairly long pedigree for a software company. We've been going quite a long time, and we're actually an American company. I'm based in London, and then we've also got offices elsewhere around the world. We've got lots and lots of users of the software in some very, very different organisations, where, as you can see, we're currently used by a fairly high percentage of the Fortune 100 and Fortune 500 companies. And we do a lot of work with academia. We're talking lots of MBA courses and also various other kind of undergrad and postgrad courses as well around the world. So we're kind of a software company. That's how we kind of started off, but then we also do lots of training and consulting for customers as well, kind of helping them to implement the software and really get the most out of what is some fairly powerful tools and capabilities. In terms of our clients, as I said, we work with a lot of the world's largest organisations in some very different industries. Oil and gas is the largest vertical market probably, but we work with insurance, with banking, with finance, government, healthcare, internet retail. You name it. We work with lots and lots of different organisations, and the kind of the main thing that links all of these corporations is their use of Microsoft Excel, which I'll come on to in a little bit more detail shortly. But it's not just large organisations who use the software. Many small to medium enterprises do as well. We sell to lots of consultants who maybe it's just them working as a sole trader or an individual. So the software is all very kind of scalable. It doesn't necessarily have to be used by your Googles, your Shells, and so on. It can also be used by much smaller organisations, which hopefully I'll show you over the course of today's session. What we make a set of product which we call the Decision Tool Suite. It's a toolkit of different types of software capability. Sometimes on these sessions I run through all the different pieces of software. But today we're just going to be looking at risk, which is about Monte Carlo simulation, which I shall kind of explain in more detail shortly, which works with Microsoft Excel and Microsoft Project. Just so you kind of know, there's some other tools as well. We do some optimizers. Actually, Risk Optimizer is part of At-Risk, the industrial edition, but I kind of think of it really as a separate product, so I'm not going to be talking about it here today. We've got tools for statistical analysis and data mining. We've got tools for building decision trees. We've got tools for sensitivity analysis, and obviously, you know, myself or indeed the relevant person for your kind of who looks after, or salesperson who looks after your region, would be very happy to talk about any of the other ones with anyone on the call, or set up a demonstration later. But as I said, today we're just going to be concentrating on At-Risk, which is kind of really the flagship product, if you like. And the idea about At-Risk is that it's about this Monte Carlo simulation. It's about using probability distributions to show many hundreds or thousands of scenarios to give us a probabilistic value and allow us to assign our confidence levels. But I'm going to kind of talk about all this in a little bit more detail shortly when I'm showing the software. So really the starting point for today's demo and Palisade business nowadays really is very much Microsoft Excel. A tool which I'm sure pretty much everyone on the call uses. You can use very many, lots and lots of different applications, ranging from cost estimation to risk registers to NPV analysis, sales forecasting, calculating the amount of oil in a reservoir, looking at you know, demand for energy. You know, lots and lots and lots of different applications, and a very, very useful tool that's fantastic for spreadsheet modeling. And how a regular Excel model works without At-Risk is that we kind of start off with our point estimates. So point estimates might be, you know, any one of a number of different variables. Cost and revenue are typically two of the key things from a financial perspective that people look at, but price, volume, and so on. These kind of get added in, these point estimates. So when I talk about point estimates, a single value. So you know, the cost of my new laptop is going to be £400, or whatever the point estimate is. That gets put in, and it's a single value. And so these then typically feed into a static, or what we call a deterministic Excel model. So very complex Excel models that we can build up, and from that we then get various project metrics which as organizations or individuals we're particularly interested in. It might be costs, it might be what's the start date of my project, what's the, you know, the NPV of this particular endeavor. But the kind of the issue which we have with that is, this is a quote from a statistician who kind of lived in the middle of the 19th century, is that, well, with Excel, with any kind of model, because inherently we're looking to make a predictive model about the future, you know, models are going to be wrong. The only time kind of we can be sure that when we're building an Excel model that it's going to be correct is when we're talking about something that's already happened. You know, maybe we're talking about the previous year's accounts or something like that. But when we're making predictive models, it's very, very hard. I'm sure there are some exceptions to this rule, but it's very, very hard to make an entirely accurate Excel model, because of course the future's uncertain. We don't have any control over what happens in the future. We can make some guesses, we can make some estimates, we might be reasonably confident in our estimates, but because we don't exert control over the future, and indeed because we don't have a time machine, you know, we can't be sure that our models are correct. So what we're kind of looking to do really, well, a few issues with deterministic modeling here. You know, how can we be sure that our estimates are accurate, and so on. Actually, what I'll do, so I don't need to kind of like read out every single word on this PowerPoint, I will, along with the link to the recording, I'll also send around this PowerPoint as well. So if anybody wants to, they can kind of refer back to it later on. But the lots and lots of issues with deterministic modeling, and I kind of wanted to give I suppose a little example of a deterministic kind of calculation. So I work in an office which is about 15 miles from my house. Half the time I cycle to work. I quite enjoy cycling, and when I cycle to work, I can be reasonably confident within a fairly small envelope how long it's going to take me to cycle to work. If I have a very good day, if my legs are feeling kind of up to it, and there's wind behind me, then I can do it in kind of, I don't know, something like 41, 42 minutes, something like that. If I'm a bit tired, on the way in it might be 45, 46 minutes. On the way home it's generally a little bit more, because there's more kind of uphill on the way home, so it's maybe more like 50 minutes. But when I drive to work, I'm kind of like northwest suburbs of London, traffic hell. There's lots and lots of cars on the road, and there's a considerable amount of variation in the amount of time that it takes me to get to work. So I've worked at Palisade for the last 6 years. And I travel quite a lot for business, but I reckon I've probably driven to work maybe 300 or so times in that last 6 years. And so what I've got on the screen here is some kind of like example data of how long it takes me. Now, I haven't actually sat down and recorded the journey time of every single journey to work. I'm not quite that kind of geeky, if you like, but I kind of just built up some data here to kind of illustrate some of the variation. On a very, very good day it might take me 30 minutes if there's school holidays and there's absolutely no traffic and all of the traffic lights are green. But on a bad day, if the school traffic's a nightmare, if it's really wet and there's an accident or whatever, it can take 2 hours or more. And so what I've got here is some sample data. And the reason I'm kind of showing this is because I kind of wanted to illustrate what a probability distribution is, because what we're talking about with that risk is the use of probability distributions to capture uncertainty. And so the uncertainty which I'm talking about when I talk about my journey time to work is how long it takes me. And I'm sure this is a fairly common thing for most people who drive to work, how long does it take to get to work? And so if you were to ask me, I say, well, maybe my kind of average time, my average journey time is around about 55 minutes, but there's a considerable amount of variation around that. And so actually, if we took this data and then we converted it into a kind of like a nice convenient graph format, it might look something like this. I kind of mocked this up myself, so it's probably not exactly like this, but it's it might look something like this, where along the x-axis down here we've got what my journey time is, between about 30-35 minutes, going up to somewhere just over kind of 2 hours on a bad day, and this is showing the frequency of any of those time periods. And so what you can see is that maybe if I show it down here, this is the average. My average journey time is about 55 minutes, but of course there's a huge amount of variation either side of it. Now, why am I talking at great length about how long it takes me to get to work? Well, of course this graph here is an example of a probability distribution. So a probability distribution is a way in which we would show two kind of different dimensions or angles on a variable. And so the first would be the range of values, which is what we've got along here from down here on the x-axis, and then the second is how likely they are to occur. And so the higher the bars are, the more likely a given scenario, or in my case a given journey time to work, is going to happen. So thankfully these kind of like outliers down here, which we would call the tails, are considerably less likely than this area here. Otherwise I'd probably look for a new job, or maybe think about moving house so I was closer to work, or indeed cycle to work every single day if my legs could stand it. So that's an example of a probability distribution, and the reason I'm kind of talking about this is because when we then think about the models that we build in Excel, when we talk about the forecasting models which we build in Excel, there's often uncertainty amongst the variables which we're putting into our model, and that's what we're really looking to capture with that risk. And so they might be uncertainty around about cost, about revenues, about whether or not various risk events happen. It might be bad weather delays, it might be earthquakes, it might be terrorist attacks, whatever the kind of the risks are in a particular field. It could be durations, how long a particular task takes, like my journey time to work. And so we have all these probability distributions which kind of exist everywhere. In the future, we can try and kind of capture them and characterize them. But how does that kind of fit in with my laptop, with Microsoft Excel? And the answer is kind of it dates back to, well, modern kind of Monte Carlo theory dates back to the end of World War II, something called the Manhattan Project, which was about the atomic bomb and so on. And one of the nuclear physicists who was working on the atomic bomb was investigating something about radiation shielding. So specifically how far a neutron is likely to pass through a particular given material. And what he realized was that there was lots and lots of uncertainties around the thickness, the speed, and so on. And he couldn't compute what the actual likelihood was, or the probability, or the distance that it would travel via normal means, because there was lots of uncertainties and variables. And so what he had the idea of doing was, instead of trying to calculate it by working out the percentages and so on, and multiplying all the different factors together, was that he would instead try and simulate it. So he'd look to simulate the occurrence of these events rather than trying to calculate them directly. And in simulating them, he would then observe the results, and then he would use that as his for his research. And so the name Monte Carlo was chosen because one of their uncles used to gamble quite heavily at a casino in Monte Carlo, and so this idea of the roulette wheel, and so a roulette wheel is traditionally has got 49 numbers on it, including 48 numbers, and then the 0, and so you can work out that you've got a 1 in 49 chance of hitting any particular number on a roulette wheel. But of course, when you start to build large models where you've got lots and lots and lots of different uncertainties, trying to kind of look at all the permutations and computations becomes very, very difficult. And so with the aid of computing, back then very, very large computers, now obviously much smaller tablets, mobile phones, etc. It's now possible with modern computing power to run these simulations, to look at scenarios, and that's what Monte Carlo simulation is. And so how at-risk kind of brings that all together is that it applies the principle of Monte Carlo simulation, which is this sampling of lots and lots and lots and lots of different scenarios or numbers from probability distributions, and puts them back into Excel. So how does that work exactly? Well, I'm gonna you'll probably be pleased to hear I'm going to actually start showing the software quite shortly, but the general principle is that you build a model in Excel, or you apply the software to your existing model. We find out what components or what inputs in the model are uncertain in some way, and then we replace that uncertainty with probability distribution. So my journey time to work, in my original model I might have said, okay, so it takes me 55 minutes to get to work, but instead I would have a probability distribution for the amount of time it takes me to get to work instead. And then what that basically is then doing is it's then taking samples, so it's just then endlessly recalculating over and over and over and over and over and over again different scenarios from the probability distribution, and then finally at the end of it we get to see our output scenario. So if we go back to this same idea of the Excel model, up here we've got at-risk installed because we've got this little Excel at-risk toolbar on the Excel sheet. We start off with the same inputs to our model, so volume, price, cost, and revenue for the example here, but instead we show these as probability distributions. These then feed into the same Excel model. We run a Monte Carlo simulation where at-risk takes thousands or tens of thousands of different scenarios from each of those inputs, and then finally at the end of it our project metrics are then displayed in ranges, so we can see what the distribution of outcomes are, and also things like key risk drivers, tornado diagrams, and so on. So lots of kind of like things here about what the kind of benefits of at risk are, some of the things that or some of the things that we get to see from the software. And as I said, I'll send this presentation round afterwards. But lots of different kind of benefits that we get from the software. We can correlate things, we can do sensitivity analysis quite easily, we can start to control risks in a better fashion, and so on. But I think now it's probably high time we actually took a look at the software rather than concentrating on PowerPoint. So thank you for your patience in kind of listening to this a little bit. As I said, I wanted to give a little bit more of a kind of like an in-depth introduction to Monte Carlo and probabilistic analysis than normal for people who aren't really sure about how it all works. So now we've talked about the theory, let's look at how it would actually apply in practice. So first of all, regular viewers to these particular sessions, particularly over the last couple of years, we've seen a succession of pictures of me and my daughter. This is the latest incarnation, which was taken a couple of weeks ago when we were on holiday in the Canary Islands. That's obviously my daughter, that's obviously me. So I'm going to load up the software now. So if I click on at risk, then what the software is doing, it's loaded up Excel, as you can see. And what's actually happening here is that it's loading some extra functions into Excel that aren't there normally, which we then have grouped together on the toolbar up here. And so in the Excel function library, we've now got all the different at-risk functions all contained in here. So the software has kind of added these extra functions and capabilities into our model. And those functions and at-risk now behaves just like an extension of Excel. So all of the at-risk functions can be used in conjunction with our Excel model, and all the standard Excel functions, if statements, min-max functions, sum ifs, lookup tables, etc., can all work in conjunction with at risk. So I think the first thing that I'll do, I'll actually just run a very, very quick simulation. So when I'm talking about this idea of Monte Carlo simulation, and when I'm building up the model, you'll have an idea of the sort of thing that we're going to end up seeing. And so this is just a little profit and loss model, which I'll kind of take back a few steps in a moment. But I'm just going to click on Start Simulation, and what at risk is doing here is it's just showing me 1,000 scenarios for my profit and loss, rather than one scenario or three scenarios. So I can very, very quickly see that there's an 18% chance of losing money on this particular venture. So that's what we're going to be working towards. So I'm going to take it back a few steps. I just wanted to kind of give a little quick simulation so that you could kind of maybe have that in mind when you see me kind of building up the model over the next few steps. So whereabouts are we? Okay, so this is a stripped down version of that same model at the moment. Obviously, with Excel, there's thousands of different types of models that you can build. I always, or pretty much always, start off with this particular model because it's a very nice, easy one to understand. I don't have to talk for too long about the structure of the model, and it's it's a fairly generic model that's common to many industries, which is where we have a selling price, we have a number of units sold, we have a unit cost, and then from that we then derive a revenue figure, which is our price multiplied by the units sold. We have a cost, which is the units sold multiplied by the unit cost, and then finally at the end of it we have a profit and loss figure here, which in this particular case, in this static or deterministic model, we're forecasting that we're going to make a profit of $11,916,000, so just under $12 million. Now, of course, as I was kind of saying in the introduction, a large part of the problem with Excel modeling is that this doesn't really take into account any uncertainty. What happens if our selling price is lower? What happens if a new competitor enters the market? What happens if our unit costs increase for some reason? What then happens to our profit and loss? Is the actual profit that we're going to make going to come anywhere near to 11.916 million, or are we going to be considerably out? And from a business perspective, is this robust enough in order for us to invest in this particular project or sales item? So as I said, the model itself is kind of irrelevant. I'm sure there's cost estimators on here from different industries, risk managers, financial forecasters, petroleum engineers, and so on. Who you've all got your different Excel models, but the methodology is very much the same, which is that we take a model, we identify elements which are uncertain, we replace those elements with probability distributions, we run a simulation, and then we kind of analyze and interpret the results. So this particular model here has got three inputs which are really uncertain. So selling price, unit sold, and unit cost, and these are just kind of calculations which then derive from those three inputs. So first thing that we're going to do here is we're going to go back to our sales manager and our procurement team and get them to give some degree of kind of uncertainty or a range of values as to what those inputs could actually turn out to be. So for each of these three inputs, we've now been given a minimum, a most likely, and a maximum. And this is something which is called a 3-point estimate, which I'm sure many of you are familiar with. And so, a 3-point estimate is now enabling us to see what the values are here. And actually, if I just do that, I guess, then I can kind of do some very rudimentary analysis here as to what my profit and loss is going to be across a range of values. Where in the best case, well, I suppose actually what you're looking at here is a minimum selling price is on one side of things, but actually maybe I should be combining a minimum selling price and a maximum unit cost in order to kind of see the worst case scenarios. But I'm gonna kind of ignore all that kind of deterministic stuff for now, because what I'm going to do is I'm going to use these minimum, most likely, and maximums in order to then drive probability distributions here. And so if I click define distributions, this is a distribution for selling price. This is the first thing that I want to model some degree of uncertainty around. And we have lots and lots of different types of distributions in at risk. 70 or so, 74 maybe, I'm not quite sure the exact number. I should really look it up one of these days. But we've got lots and lots of different types of distributions, and the different distributions behave in different ways, and picking the right distribution is can sometimes be challenging, which is why we do training courses to help customers kind of understand the differences between the main ones. But generally speaking, the distributions are broken up into two different camps. So you have your continuous distributions and you have your discrete distributions. A continuous distribution might be an example, my journey time to work would be a good example of a continuous distribution. So it's, there's a range of values, and anywhere along that range is theoretically possible. And so you could break up my journey time to work into minutes, into seconds, into milliseconds. You could kind of splice that time down, ad infinitum until ever smaller units of time. And any of those would be theoretically possible. And so a continuous distribution is one where we have a continuous range, and anything along the range is possible. And so for things like selling price, units sold, selling price and unit cost, certainly those would be good choices. But for things like risk events, we typically use discrete distributions, where we want to know how many times does this event happen, does this risk happen, yes or no, etc., etc. But for now, I'm going to use continuous distribution. On this tab here, we've got the most commonly used ones by our customers have been put on this tab to give you a kind of like a starting point. Different industries, different applications tend to follow specific use of distributions. And when we talk about 3-point estimates, most commonly you'd use something like a PERT or a triangular distribution, because these distributions conveniently use the same parameters as our 3-point estimate here. So as I said, I could probably talk about distribution types for a good 3 or 4 hours, and I don't want to get too focused or too bogged down on the details of that now, because otherwise we're not going to have time to show the rest of the software. Incidentally, as you've probably noticed, brevity is not one of my strong points, so sometimes I do tend to talk at length about particular things. So I'm making a conscious decision not to talk for too long about choosing the right distribution, so at least then we've got time to see the rest of the software. So what I'm going to do, I'm going to select a PERT distribution as my as the first distribution that I'm going to use. So as I said, the parameters for a PERT distribution are the same as my 3-point estimate. So, oops, no, don't want to do that. A minimum, most likely, and maximum, which is what I've got here. So if I just click this little button here, which allows me to assign Excel cell references as arguments, then I go 1, 2, 3, hit the enter button, and now what I've got a distribution for selling price that has been based on these 3 values down here. So here we've got a minimum selling price of $95, which is this point down here. We've got a maximum of 110, which is this point here, and then we've got a most likely of 100, which is this point here. So I'm just going to click OK, and I'm just going to start tapping the F9 button, because what you can now see is that in this cell here, rather than having a fixed value for my selling price, which is I think 102 or something originally, what I've now got a dynamic value for the selling price, because what's happening is that at risk is taking samples from that distribution, it's feeding them back into Excel, as you can see, and then what Excel is doing is it's then recalculating the selling price, the sales revenue, and at the end of it my total profit or indeed my total loss on this particular venture. So if we talk at some detail about what that actually means. So this is a probability distribution. This is an example of a probability distribution. As I said, the minimum is 95, the maximum is 110, and the most likely is this 100 here. And so when I was hitting the F9 key, what that risk is doing, it's then starting to take samples, or scenarios you might prefer to term them, from within this distribution, and it's then putting them back into my Excel model. And the way it's generating those scenarios is in 2 ways. Well, first of all, there's a kind of random number generator that's contained within the software, this kind of Monte Carlo simulation or Latin hypercube in this particular case. But and what it's doing, it's that number generator is then taking samples in conjunction with the type of probability distribution. So it's taking samples which are based on the shape of this distribution. And so what we can see is that these areas out here, kind of off towards the extremes of the distribution, these are what we would call the tails. So these events are less likely than this kind of like this big area here. So essentially the higher the graph is at any one point, the more likely it is that the samples are going to come from there than they are from here. And so that's kind of really designed to reflect the reality of the situation, because when we ask for minimums and maximums, we're talking about extreme circumstances here. So we're saying, okay, the absolute minimum is 95, but that's extremely unlikely. The absolute minimum is 110, but we have all these kind of scenarios in between, and so the software is basically going to be taking samples over and over and over and over and over again from this distribution, putting them back into the spreadsheet, and then it gets kind of recalculated. Now, an example of a different type of distribution and kind of how that could kind of impact upon things. Actually, if I just clear this off a bit. So first of all, if I backtrack a moment and say, okay, so what's the probability that my selling price is going to be more than $100 based on these inputs that I've given down here? Well, okay, so there's a 58% chance of that. And so what the software is going to do, 58 times out of 100, it's going to take samples from somewhere in this shaded area of the graph here. What's the probability my selling price is going to be more than 105? Well, okay, there's only an 8% chance of that, and so there's only an 8% chance that the software is going to take samples from between 105 and 110, and the other 95% of the time it's going to take them from between 94 and 105. And so we can, these are what we call confidence levels. So we talk about confidence levels quite a lot with at risk, and these values up here are the confidence levels which we would ascribe to any particular input or output. And so when we talk about there's a 5% chance, what we're saying here is that we're 95% confident that our selling price is going to be somewhere between 95 and $105.7 and there's a 5% chance it's going to be more than that. So when we talk about confidence levels, we typically talk in terms of p-values. So we'd say that the 90, to be 95% confident, we call that the p95, which is something that we'll come back to over the course of the demonstration. So what I was going to do, I was going to add an overlay to show you a different type of distribution, because of this, the three parameters which we've got here on a PERT distribution, we have a bias towards this particular point. So the samples are more likely to come from this area here than the tails, because of the shape of the distribution. Whereas if I chose, say, a uniform distribution, actually you can see that here there's only two parameters. We just have a minimum and a maximum, and so the minimum is the same, 95. The maximum is the same, 110. But you can see that without that kind of bias, we have this curve here is the same height from start to finish. So my samples are just as likely to come from here as they are from here, as they are from here, as they are from here, and so on. And so you can see up here that correspondingly there is a much higher weight given towards what were previously the tails than there are with a uniform distribution. So different types of distributions are then going to have an impact on the results that you get in your model. So choosing the right distribution becomes quite an important thing, but it's also quite a pragmatic process as well, and indeed it's better to almost choose the wrong distribution in as much as there is a wrong distribution than not to do it at all. So that using some of the common ones, using some common sense guidelines, there's probably 4 or 5 distributions that are perfectly suitable for the vast majority of cases. So anyway, let's clear that overlay off. Click on OK, just to speed things up a little bit. I'm just going to drag these across here, and now we've got a distribution in 1, 2, 3 cells, which have now been based on the 3 cells below. So as I said, the software functions just like Excel normally, so you can do your kind of drag and drop or copy and paste if you like. So it's also brought across the formatting from Excel. So let's just change this to a number. Of course, technically this should really be maybe a discrete distribution rather than a continuous distribution, because you don't tend to have decimal places for units sold, but that's kind of like a minor detail that I shan't go into in too much detail now. So I've got a distribution for my selling price, for my units sold, for my unit cost. And now what I'm going to do, I'm going to say that the profit and loss is my output. This is my risk output. This is the thing which I'm particularly interested in seeing what happens when all of these different units, all of these different inputs combine and show different values, etc. So sorry, I think I need to. What I'll do, I will stop now and again to check for messages. So it might be that people have got questions, so please just kind of ask any questions. We've just switched from using WebEx to GoToMeeting, and so I can't always see whereabouts questions are, so I will endeavour to to find these. If you've got any questions, please just use the chat panel. And yeah, as I said, I'll go and check that from time to time. But it doesn't look as though there's any questions at the moment. But if you do have any questions, just ask me via the chat panel. So as I was saying, so this is the metric which we particularly want to see what happens. And so what I'm going to do, obviously, because all these inputs change, each time I'm pressing F9, the profitability changes, sometimes positive, sometimes negative. And so what I'm going to do, I'm going to ask at risk to show me what happens in 10,000 different scenarios. So what we do with that risk, we run a simulation, but that simulation is made up of a number of iterations. So each iteration is one of those samples. So each time I press F9, that's the equivalent of 1 iteration. And so what I'm going to do, I'm going to ask at risk to take 10,000 iterations over the course of a simulation. So if I click Start Simulation, then what you can see, actually if I pause that for a second and move it out of the way, actually let's make it a little bit smaller for now so you can kind of see what's happening as it's going on. Whereabouts are we? Oops, making it too big, too small, losing control of the demo. Hereabouts. Okay, so what you can see in the background, that's the kind of the simulation process. So at risk is taking those samples, it's putting them into Excel, and then Excel is then recalculating over and over and over and again. And what it's recalculating is this. This is a histogram. So this is showing me those 10,000 scenarios, and so this is running in demonstration mode, so it runs pretty slowly. So if I just speed it up a bit, okay. So now what we have here, we've got 10,000 scenarios for our profit and loss rather than just one scenario. So originally, our original forecast before we had any uncertainty or any probability distributions in there was 11,916, I'm pretty sure. A figure which we've got a 3.5% chance of achieving or bettering once we put in our probability distributions and run a simulation. So all of a sudden that particular venture isn't looking quite as rosy or guaranteed as it was when we were kind of like viewing things through a deterministic filter. You know, once we start putting some uncertainty into here, all of a sudden this venture looks decidedly less appealing. If we want to find out what the probability is that we're actually going to lose money on this venture, well, we've got an 18.4% chance that we're gonna end up losing money on this particular venture, and we can grab these things. These are called delimiters, by the way. That's the name for them, and we can then use them to calculate what our confidence levels are at any given point. So we talk about the P90, our 90% confident. You know, we can be 90% confident that we're going to achieve less than 9,850, or maybe that's not necessarily the best way of looking at things, but that would be our P90 in this particular model. So what this is showing along the x-axis is that's the range of values between somewhere between a minimum value of 11.6, a loss of 11.6 rather, and in the best case scenario we make almost just over $17 million. And we can get lots of statistics here. You've got the P10, the P50, and the P90 here. Histogram is just one way of kind of displaying this data. There are kind of other options here. If some people like histograms, some people prefer these things cumulative curves or S-curves or cumulative ascending curves, whatever you want to call them. But the information shown is exactly the same. It's just displayed in a different way. So at its most elementary, that's what at risk does. We take a model, we replace the uncertainty in that model with probability distributions. They help us to capture that uncertainty. We run a simulation and then we look at the results. But there's lots more that we can do with it besides. Now I see that I now have some questions in here, so at this particular point I will just stop and take a look at the questions. Okay, so question number one. I don't know if everyone on the call can see these questions or not, or if they're hidden. So I'll read them out. Do you use the same probability distributions for all parameters? For example, if you use PERT for selling price, would you use the same for units sold and unit cost? Thank you, Joseph. No, not necessarily. When you can mix and match distributions, according to what the best or the most appropriate one is for the input. So really, the choice of distribution should be driven by the type of data that you've got, and so logically from that, it kind of follows that the same distribution isn't necessarily appropriate for all things. So you can mix and match, and indeed I'd strongly recommend that you kind of mix and match your distributions and use the one which is the most appropriate. Someone asked, do you need to set distribution for each of the variables? Yep, I did that. But you don't need to. You would the distributions which you would put into your model are the ones where there's any uncertainty. If there's no uncertainty, let's say you've got a predefined contract with a supplier in this case, and your unit cost isn't going to change, then you wouldn't put a distribution there because there's no uncertainty. Distribution definition as well as I think I kind of covered that. Someone's asked, gosh, there's lots and lots of questions today actually. If there's 10,000 iterations, is the final distribution an average of all 10,000 distributions? No, absolutely not. So the whole idea here with at-risk, with Monte Carlo simulation, with probabilistic analysis, is that we get away from this idea of the average. We're not talking in terms of the average when we're talking about at-risk. Of course, you can use at-risk to calculate the average. In this particular case, my average profit is going to be $4.127 million. But that's not what we should be doing with the software. What we're doing with the software is we're using it in order to find out our confidence levels. So, we have this extra dimension, which is that, we're 90% confident of this, we're 10% confident of this, rather than just having a fixed value. So we get to see, the range rather than a deterministic single point estimate. Someone says, I'm finding it difficult to follow the simulation. I'm not sure what you mean. Do you mean that you can't see it on the screen, or you don't understand the process? I'm not quite sure about that. So I'll talk a bit more about simulations in a moment. Someone's asked me to show the impact of correlations. So yes, I shall do that very, very shortly, Mr. Bartlett. Someone else said, let's just see. If we were to understand this chart, does it show that in 10,000 samples, there's a 71.6% chance that we receive up to 10,000 of profit? Yeah, actually, I suppose technically there is. So there's a 71.6% chance that we're going to be above zero, but less than 9,850. So yeah, there's a 71.6% chance that our profits are going to be, somewhere under 9,850. But then there's an 18% chance that we're going to have losses, or a 10% chance that our profits are going to exceed this value here. So so I'll talk about correlations in a little while, but I'm just going to kind of move on, and I'm going to talk about some of the other kind of results, etc., that we get from the software. So what we're going to talk about now is tornado charts and sensitivity analysis. So once we've run a simulation, then one of the next questions is, which factors are the most significant? Which inputs are having the biggest impact on our output? And before I kind of talk about this, I want to make a little bit of a distinction so that it's clear right from the start. And that is that, well, we've kind of not got the best product name, or certainly the most accurate product name, because when we talk about at risk, people or lots of people assume that what we're doing, we're talking about risk, we're talking about bad things that can happen. But actually, technically speaking, what we're actually doing with the software is we are modeling uncertainty, and that uncertainty, that's uncertainty or variability, the variability around a particular input. The terms risk and the flip side, opportunity, are very much subjective terms that are relative to the person who's building the model. And so so I prefer to use the term uncertainty or variability, and so really at risk should have been called at uncertainty, but I guess it's probably not as catchy a name, because of course one person's risk is another person's opportunity. If the price of gold increases, and you're a jeweler who kind of needs it as an item, as a material in which to build or to create exotic jewelry pieces, then the price of gold increasing is potentially a risk to your business, because the price of gold goes up, you have to put your prices up, and then you maybe sell less. But if you're a gold miner, then the price of gold increasing, that's not a risk, that's fantastic, that's an opportunity. So try and think in terms of uncertainty rather than just risks. And I think it's quite a useful distinction when you're looking at this from an organizational perspective, so that people don't just think, right, at risk, okay, that's just about the risks to our business, because it's about quantifying uncertainty and then making better decisions around that, under uncertain conditions. So, a little digression. I'll get down off my soapbox, and I shall now talk about tornado charts. So, of course, this is it's a very Mickey Mouse model, where I've just got three inputs to my model. I've got unit cost, selling price, and units sold. But of course, the type of models that you probably build yourself might have hundreds or thousands of different inputs, and so these tornado diagrams are a really good way of being able to focus in on the factors which are the most significant or the most critical in your model. And so what this is showing me, this tornado chart, it's showing me, so a tornado chart, the idea is that it kind of looks like a tornado. You have, when it's spinning at the bottom of the ground, it's, the diameter is relatively small, whereas when it kind of goes up and up and up, I'm actually, idiotically, I'm actually spinning a tornado on my hands, even though I'm doing a web demo where no one can see me. I'm kind of spinning a tornado. So if you imagine a tornado, at the bottom it's small, at the top it's widest, and that's what these graphs show. And so what this is showing me, that the thing at the top of the graph, that's at the top of the tornado, is the thing where the variation over that input is the most significant to my overall model. And so this is saying that the unit cost is the thing which is the most significant in my model. And so if I just drag that out, let's talk about what that actually means. So this is a scatter plot, and on this scatter plot are shown all 10,000 of those scenarios plotted on here. And so along the x-axis we've got what the unit cost was. So in this case the unit cost was between 90 and 110 or whatever, and then along the y-axis we've got what the corresponding profit or loss was at a given point for our unit cost. And so if we look down here where where our unit costs are at the low end of things, guess what? Our profits are relatively high, whereas when our unit cost increases, so our profitability tends to decrease, which of course is what we'd expect. But it's still nice to be able to kind of look at those relationships rather than it being a kind of like a black box. And we get things like our correlation coefficients out of here as well, which is quite nice and quite useful. So this is a way of showing what the relationship is between the input and the output. If we look at, instead of say selling price, you can see it goes in the opposite direction. There's not, it's got a lower correlation coefficient here, so the curve isn't quite as steep. So that one kind of went more like that, whereas this one's a slightly flatter curve. Selling price is low, profits are low. Selling price is high, profits tend to be higher. And for the sake of completeness, you can see down here that this little bar is very, very small by comparison to the two above it. And so what that implies is that the actual number of units sold is not really a particularly large factor in terms of whether we're making a profit or loss. And so if we drag that out and take a look, you can kind of see here that there's very, very little relationship between the number of units sold and whether we make a profit or loss. It's kind of all about the selling price and the unit cost. And there's different ways of showing this information. You get spider graphs, which kind of, you've got a percentile of the input, and then you've got what the value of the output is as well. But those are quite a useful way of being able to focus in on the factors which are the most important in a model. So some more questions. Okay, okay. Can you go through the simulation steps again slowly? I'll probably do that again a little bit later on, Richard. But because I've already been talking for 53 minutes somehow, and this particular session's only 90 minutes, there's still an awful lot to cover. So actually, what I'll do, as I said, I'll send around the link to the recording, and then you can kind of watch it at your own leisure and kind of like press pause and view it again and again, however many times you want. Okay, in terms of the scatter plots, the way I just derived those, I went into my tornado diagrams, and the way I did it, I actually just left-clicked with my mouse and then just dragged it out from the tornado. You could set it up down here using this kind of scatter plot option, but then that's slightly more cumbersome, so I just kind of did it like that. But you can actually set up a scatter plot with any input distributions that you want to. Okay, so next thing I want to talk about is something, well, someone asked me about this earlier on, is correlations. So the idea with correlations is that where sometimes we want to look to build relationships between inputs. So the whole idea of at-risk is that we want to use it in order to capture uncertainty, and that we want to make our models kind of more meaningful and more realistic. And so something that's really, really important when we're building our models is to make sure that we take into account any relationship between inputs and capture those in our model. As an example, well, this particular model here, let's say there's almost certainly going to be a relationship between our selling price and the number of units sold. So, if we put our prices up, then we would typically expect the number of units sold to move in the opposite direction in most cases. Of course, some things, there's not the same elasticity or sensitivity going on, but for most cases, most industries, if we put our prices up, then the number of units sold is inevitably going to fall off in the opposite direction. And when we build up models, if it's a straight line kind of linear relationship, we could just use something like an if statement to show the links between those. But when we're talking about kind of probabilistic modeling and uncertainty and quantitative risk analysis and so on, often it's a non-linear relationship. There's not a if our price goes up by this, our selling price is going to fall by this amount in a kind of like a linear model. Sometimes it's a bit more of a fuzzy relationship, and so when we build kind of models with that risk, what we do is we use something called correlations in order to capture that relationship. So what I'm going to do, I'm going to click the Define Correlations button, and I'm going to say that I want to add a couple of distribution inputs to correlate. And so the ones that I'm going to use are my selling price here and my units sold here. And so now I'm just going to click this little button down here, which I'm hovering over it, and you can see it says show scatter plots for correlation matrix. And so if I click that, this is now kind of showing me visually that my units sold and my selling price. And so correlations can be either negative or positive. Correlations are always between -1 and +1, any kind of value in between. Often if you've got historic data, you could use something like the correl function in Excel to determine the correlation coefficient. But lots of companies break things down into bands. So rather than getting kind of too hung up on whether something is a 0.2 or 0.18 correlation coefficient or whatever, often companies just say, okay, so a mild correlation was maybe 0.2, a medium strength is 0.4, a reasonably strong is 0.6, a very strong correlation is 0.8 or whatever, and kind of just break it down into bands. As I said when I was talking about the choice of distributions, getting hung up on the absolute perfect correlation coefficient probably isn't, is it really going to make that much difference whether it's 0.7 or 0.71, bearing in mind that your model is going to be wrong anyway, because we're talking about the future and uncertainty, where don't get too worried about getting the exact correlation coefficient. It's more important to make sure that they exist in the first place, and then to give some idea of the tendency, whether they're positive or negative. So in this particular case, if it was a positive one, then I put my selling price up, then my units sold is also going to increase, which is of course nonsense. So unless maybe you're kind of Prada handbags or some very, very kind of unusual brand such as that, where actually that something acquires a certain cachet for being exclusive, and so sometimes the demand might increase even if maybe the unit sold doesn't. But in this case, I'm going to say that I want there to be a negative relationship, where if I increase my selling price, my units sold is going to decrease, and I'm going to put it in as a reasonably strong negative relationship here with a correlation coefficient of -0.8. So if I now click on OK, At-Risk is now asking me whereabouts I want to put this correlation matrix, which frankly it doesn't matter, it could be anywhere on my spreadsheet. If I just put it down here, let's kind of lose this comment. Let's hide the comment. And now what I've got here is I've got a correlation matrix. I'll just expand it out a little bit so you can kind of see what's going on, which now shows me the correlation between those variables. And so what At-Risk has done, actually I should probably have talked about this a little bit more at the time, but when we build in distributions, At-Risk has added these extra functions into Excel, and that's what you then see in the formula bar. So for unit cost, I've got a distribution with a minimum value of the value in E7, the most likely in E8, and the maximum in E9, and that's the function equivalent of this distribution here. And so what's happened with the two variables which I've just correlated, at risk has now added an extra bit to the function, which is saying, okay, so for selling price and units sold, when you run a simulation, you need to make sure that you look at the value in this correlation matrix here, and then make sure that those two variables are kind of linked together. And actually, for this particular instance, because the units sold didn't really have much of an impact anyway. I could run another simulation and probably not see a huge amount of difference between one and the other. So whereabouts are we? Okay, all right. So the chance of losing money has decreased slightly to 18%, bizarrely, but my maximum value has gone down, etc. I'm not quite sure exactly how this correlation or what the kind of impact of this particular correlation is, but that's the kind of the general idea, that you look to find the inputs where there's a link between them, you correlate them and put those into your model. And of course, it doesn't have to be a little 2x2 matrix, which is what we've got here. You can have a big 10x10, 20x20 matrix, and so on, with lots of inputs. So I'm going to delete my correlation matrix for now. I'm going to just hide those away for a little bit. And no, I'm not. I'm going to bring them back, and I'm going to talk about scenario analysis. In fact, so I'm flip-flopping all over the place. I'm going to talk about scenario analysis, but I'm going to use something called stress analysis. So when we talk about scenario analysis, what we're then looking to do really is to see what happens in the event that some of our inputs change, or we want to see what happens if our inputs are at a given point. What does that then do to our output? And the two of the main ways which we can do this with at risk are the stress analysis feature and the at-risk sim table. And I'll talk about the stress analysis first. So what I'm going to do here, I'm going to use the stress analysis feature to show me what would happen in the event that let's say my selling price is lower than expected. So let's hypothesize and say that there's a risk which or there's some uncertainty, but in our case there's a risk that a new competitor might enter the market and might swallow some of our market share, or we might need to compete on price in order to keep our customers. And so in the normal run of things, when we kind of run a simulation, we would call it our baseline simulation. Our baseline simulation here, when we kind of run a simulation, we've got an 18% chance or whatever of losing money. And what the software is doing, for each iteration, it's taking samples and it's taking them from absolutely everywhere in this distribution. So from here, 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 and so on, and over and over and over and over again. But when we talk about the stress analysis, what we have the option of doing is to see what happens to our model if we just look at a particular part of this range. And so what I'm going to do, I'm going to use the stress analysis to see what happens to my profits if my selling price is at the low end of things. So at the extreme end of things, I'm going to say, okay, all I want to do, I want to see what the values are for my profit or loss if my selling price is in the bottom 10% of cases. And so when I set it all up in a moment, what's going to happen? Well, actually, I shall do it now. If I go stress analysis, so I want to look at the whereabouts are we? The output in cell 6, and I want to see what happens when my selling price is in the bottom 10% of cases. So we can stress things at a high level or stress things at a low level. I'm sure many of you will have heard about stress testing with kind of banks' capital adequacy ratios and so on. It's quite a hot topic in terms of financial regulation. But the idea of a stress test is to, or stress analysis is to find out what happens at the extreme end of things and to see how that impacts upon our model. And so when I click on OK and then Analyze, at risk is now going to run 2 simulations rather than 1. So in simulation number 1, once it's kind of all finished, this is my baseline scenario for my profit. 18% chance. These numbers vary incidentally because the starting point on the algorithm changes each time I run a simulation. But I can maybe, if I've got time at the end, I'll talk about how you can fix that. But this is the baseline profitability for this particular venture. But now, if I look at the stress scenario, you can see a different picture. So the red curve, reasonably kind of, we're confident that, in most cases, in maybe 4 out of 5 cases, we're going to make at least a profit on here. Whereas the blue curve, you can see that actually it's kind of shifted across to the left-hand side. And actually our probability of losing money on this particular venture increases drastically to almost a 1 in 2% chance, 1 in 2 chance that we're going to lose money if our selling price is in the bottom of 10% of cases. So this is kind of quite a nice elegant way of being able to show what happens in the event that the brown stuff hits the fan, and our selling price is low, or our units sold is low, or our costs are higher than expected, our revenues are high, whatever it is that we're looking to model. This is a good way of being able to show what happens at those extreme circumstances. And then of course, we can, we or you as an organisation or business can then talk about whether that's an acceptable, gamble to take. Given taking that into account, are we able to withstand that? Do we have enough money in the bank to kind of, swallow that kind of loss, or is it going to, is that going to have a catastrophic impact on our business or whatever? So stress analysis, scenario analysis is a really, really powerful tool for being able to see what happens in the event that some of our inputs turn out to be better or worse than expected. So that's the stress analysis. So I shall lose that for now, and I'll just talk about an alternative type of scenario analysis. So let's just make that neater. And that's something called the at-risk sim table. Now, before I do this, I'm just going to look at my questions panel. Someone said, can we fix the units sold to be measured in units instead of dollars? Yes, you could do that. Does it show which factors? Does the model show which factors causing the most impact to the outcome? Well, yeah, that's what the tornado diagrams are hopefully doing. Someone's had to go because they only had an hour, so I need to send them a link. I shall do that. Let's see, queuing, priority queuing. Yes, you could do that with discrete distributions, but I probably haven't got time to kind of go into that now. But yeah, that's certainly something you could do. But Neha, if you want to send me an email afterwards, I'll get your kind of sales rep to basically kind of contact you and kind of talk about that in more detail. So on that note, what I'm going to do, I'm just going to show here my. So. If anybody has got any questions, or either myself or your sales rep or whatever, please just send me an email to doldfield@palisade.com, and I will either answer it myself or get the relevant person to, and I shall also, if I can figure out how to do it, I'll also send it to everyone in the chat panel now. Good. Okay, so everyone has now got my email address in the chat panel. Okay, so I was talking about the at-risk sim table. Okay, so the sim table is an alternative way of doing this scenario analysis, and this is a really, really, really powerful part of at-risk that lots of people have got no idea even exists. There's obviously, it's a wonderful product. It's been built over the last 30 years, but lots of people kind of don't kind of take the time to explore absolutely all of the functions, maybe because they kind of feel as though they don't need to, or obviously you might not have time to do that. And so I always kind of make a point of highlighting the risk sim table as a really, really useful function in the software for doing modelling. And the idea of the risk sim table is that it allows us to see what happens if, in the event that some of our inputs change. And so what I'm going to do, I'm going to set the number of simulations up here to 3. So lots of people who use at-risk on a day-to-day basis probably have got absolutely no idea why you might want to run more than one simulation. And the risk sim table is an example of why you might want to do that. So the idea with the risk sim table, so in this particular function down, in this particular cell down here, F17, I've got a risk sim table function. What this is telling me is that in these 3 cells here, or these 3 cells are making up a table of values. And the reason I've set the number of simulations to 3 is that at-risk is going to run 3 simulations, and over the course of those 3 simulations, it's going to put a different value in this particular cell for each simulation. So simulation number 1 is going to take the first value in the table, so 0% in D16. In the second simulation, it's going to use 5%, and then in the third simulation, it's going to use 10%. And those values are going to get returned to this cell here. And the reason it's showing 0% at the moment is because I haven't started the simulation yet, so it's defaulting to the first value in the sim table. So why am I doing that? You might rightfully ask at this point. And the reason I'm doing this is because in when we ran the original simulation and we looked at the let's just show the baseline scenario, and we looked at the tornado diagram, you know, the unit cost was the thing which was the kind of the key driver here, the thing which we thought was the most important. And so what we've done, I wanted to show what would happen in the event that we could somehow secure a discount to our unit cost. So when you do those tornado diagrams, etc., you know, they're a good starting point for working out which are the kind of the elements which you want to put the most effort into controlling. And so here, I wanted to show what would happen in the event that that our procurement team could, or to try and focus the minds of the procurement team to see what happened if we could somehow secure like a 5 or 10% discount on the expected values of our unit costs. And so the way this is going to work is that in these 3 cells here, 1, 2, 3, you'll notice in the function bar that what we're saying is that we want Excel to reduce the contents of these 3 cells by the value in this cell. And so the way we've written this mathematically is we're going to multiply them by 1 minus F17. And so in the first, so what that kind of means is that in the first simulation, that if we reduce 1 by 0%, then we're not reducing it by anything, and so actually 90 multiplied by 1 is still 90. In the second simulation, we're going to reduce it by 5%, and in the third simulation, we're going to reduce it by 10%. So these 3 values here are going to be reduced by a corresponding amount over simulations 2 and simulations 3. So if you remember 90, 95, and 110. If you also remember 0% here, then let's kick this off and show you what happens. So if I go start simulation, actually I need to put updating on. Which one is that? So actually, if I do that and then pause it, and then how do I do this? I'm trying to. Okay. So I've just paused it. So we're now on the second simulation, and you can see that the values have changed. So I can't remember what it was, 90, 95, and 110 or something like that, and 0% down here. And you can see that now we're into the second simulation. Actually, those values have changed. And so those values have changed, and therefore the distribution for our unit cost has also changed. If I start it off again, and then put it back on. Oh. But I missed it. I cursed my slow fingers. But for simulation 3, that value would have changed by 10%, and these 3 values would have been reduced by 10% as well. And so the idea of doing that, of course, is that now what we can do is we can say, okay, so if we get a 5% discount to our unit cost, that's what happens. If we get a 10% discount, that's what happens. And so here now we've got the, those three different scenarios are being shown here, and so it's a really kind of quick and elegant way of showing what happens in the event that some of our inputs change. So here we've got the baseline scenario, no discount to unit cost. Here's a 5% discount. Here's a 10% discount. Our profitability is increasing, drastically. If we get a 10% discount to our unit cost, all of a sudden the future's very, very rosy indeed. We've got no chance of losing money. Even a 5% discount means that the probability of losing money on this particular venture drops to 2.4%. And so actually then we can then start to talk about things like, okay, so then maybe it's worth spending money sending our procurement team to travel to some other locations, maybe around the world, but if we do so, then we've got a higher chance of making sure that we're profitable on this venture. So it kind of enables you to really start these discussions, and then start to really kind of analyse about and talk about which decisions we want to make and which factors we want to concentrate on. So this is kind of this is all kind of like a starting point, if you like. This is very much a kind of an introduction session. As I said, different industries, different applications. You use these models in different ways, but I just kind of want to show some of the cool things you can do in at-risk, which hopefully then you'll be able to think about applying to your own models. So let's just think. Okay, how am I doing for time? I've got 14 minutes left, and there's quite a lot of the toolbar which I haven't even talked about yet, but never mind. Okay, moving swiftly on then. If you have historic data, so when we're talking about kind of choosing the right distribution, and you've got all these different distributions to choose from, how do you choose the right one? Well, quite a common thing that we can do, if we've got some historic data, then we can actually use at-risk to run some various tests to tell us what type of distribution best fits that historic data. So here we've got 100 samples. I don't know what this is for, selling price maybe, or maybe units sold of a similar product that we've sold in the past. And so if I go to distribution fit in here and then fit, then what at-risk is going to do, it's then going to look at all of these different distributions here, and it's going to fit them to that data using some various methods, etc. I'm just going to use the defaults because I'm very pushed for time at the moment. If I just click fit, then what at-risk is telling me here is that the thing or the distribution which is the best fit for my historic data is this risk beta general distribution. So the historic data is grouped together on this graph here, and that blue data there on the graph, and then this red curve which has been overlaid on top is this distribution which is the best fit, this risk beta general. Now if we kind of go down the list here, triangle, normal, Laplace, etc. You can see that the distributions become less and less suitable for my data. And so typically what you do, you'd look to choose the distribution which is the kind of the best fit or close to the best fit, and then use that. If I write to cell and then click next, as an input for your new data. And so here now what we've now got that historic data converted into a probability distribution, which now at-risk can sample from as part of our and use it as an input for our new model. Really useful stuff. Now if there's a time series involved, we would look to do it in a slightly different way, and I'm going to come back to the time series shortly, hopefully, if I've got time. But I just wanted to kind of pick up on a couple of other things which are probably kind of more important or more relevant for the majority of people here. First of all, I want to talk about risk registers. I'm going to show a completed version of a risk register. Let's just say this risk register down here. Okay, I need to be very quick about this. Incidentally, with all of these sessions, or most of these sessions, I don't know if you're kind of aware or not, but as I said at the start, I was going to record this session. And if you go to our website, palisade.com, and then you go down to training and events, and then free webcasts, and then archived webcasts, what you've got in here are lots and lots of webcasts which have been given by people in the past, talking about applications of the software in different industries, or maybe software introductions by Palisade staff such as myself. This is a really, really good resource. This presentation will probably end up in there at some point as well. But this is a really good place to kind of look if you're, if you're not sure about stuff, or if you want to find out how, okay, I work in the oil and gas industry, I want to find out a little bit more about different applications about risk. Well, here's one in here, and we've got lots and lots of them in here from different customers and so on. The reason I was reminded about this is because I remember that I'd done one about risk registers. So if risk registers are something that you're interested in, then have a look at this webcast here, because that kind of talks about it in more detail. For now, I'm just going to skim over it very, very quickly, because I wanted to show an example of discrete distributions and how we might go about using those. And a risk register is a really, really common application to business. So this is a little project risk register model that we kind of built up. We've got different risks which might face this particular project, each of which has been given a different kind of impact. And when we talk about risk registers, we typically talk in terms of two different dimensions. So the first thing that we talk about with risk registers, we talk about what the probability is. What's the likelihood that any a risk is going to occur in a given time period. So for each of our risks down here, we've got different probabilities, ranging from 50% probability that this customer is going to be particularly sloppy and give the requirements late, down to this a 4% chance of technology obsolescence, whatever that is, or 2% chance of a pollution incident. So that's the first part of a risk register. We talk about the probability, but then we talk about the impact. How much is it going to cost if a particular risk occurs, or how many days is it going to delay a project by, or what's the kind of environmental impact of a spillage, etc., etc. And lots of companies kind of do this in an average. So they typically multiply the probability by the impact to get an average. And so we've just kind of taken the most likely value here, multiplied it by the probability, and we've got an average risk figure. For here, the average risk for this particular project is going to be 52.5 million, which is based on the average. But of course, this is a not necessarily the best way of doing things, because all this is showing us is what happens in the average set of circumstances. But of course, if we look down here, 52.5 million. Okay, that's that's not an insignificant amount of money. But actually, we've got 1, 2, 3, 4. 4 of these risks alone. If any of those happen, then they're going to equate to more than 52.5 million. Let alone if lots of them happen at the same time. And so, what we do with that risk, rather than having this deterministic view on the risk register, we turn it into a probabilistic model. So for the impact, the severity, we've just got distributions, just as I had for my last model, continuous distributions to show the uncertainty around the actual impact. What we're doing here with these discrete distributions is we're looking to simulate whether or not these events are occurring or not. And so here in this particular column P, when I'm pressing F9, what I'm doing here is I'm generating lots of 1s and 0s, and those 1s and 0s are being driven by the choice of distribution, which is in this case a Bernoulli distribution. Also, binomials are the same kind of idea, which are then looking at the values here. So here, customers got a 50% chance of giving their requirements late, and so in this cell here we've got a distribution to simulate that. And so in 50% of cases the customer isn't going to give us their requirements late, in which case that risk doesn't happen, so it happens 0 times. In 50% of cases the customer is going to give us their requirements late, which means that there's a 1 there. So what we're doing, we're generating 1s and 0s to simulate whether or not the risks are occurring. So there's, this is a 50-50 chance. So this is this is exactly the same as flipping a coin in the air and calling heads or tails. You've got a 50% chance of heads, you've got a 50% chance of tails. And so half the time I'm going to get a 0, and the other half of the time I'm going to get a 1. If we go down here to say this one here, then this one, there's a 5% chance of it happening. So this bar is much higher, so there's a 95% chance of a 0 and a 5% chance of a 1. And so what we're doing here, with this particular risk register, we're now able to capture this conditional relationship between the actual impact combined with the whether or not the risk occurs and the simulated impact. So whereas here what we're saying is, if this risk occurs, it's going to be 2250, or actually here we're saying, okay, so if it occurs, we're going to simulate it as being 4764. If it doesn't occur, if we get a 0, then it doesn't get counted here. So we're able to capture that conditional relationship. So if I run a simulation, wait for it to start. Here what we've got is we've got a probabilistic risk register instead of a deterministic one. So now we can say what's our P90 risk? Okay, our P90 risk for this particular venture is $131 million. What are the key risks? Key risk is raw material delays, followed by customer bankruptcy, followed by design solution QC, and so on and so on. That was an incredibly quick introduction to risk registers. Obviously, when we've got that information, we can then, look to do things like, kind of model mitigation strategies in the same way, and find out, which strategies work best. If we kind of mitigate, we can then look to overlay, mitigation and non-mitigation, and find out what the best approaches are in terms of controlling our risks. But that's the kind of the general idea of a risk register. At-risk library. This is just a way of being able to standardize inputs across an organization. So let's say there's lots of people at an organization. Let's say you've got 10 analysts all working on different models, all of which have got oil prices and inputs. Rather than having 10 different views on oil price, the at-risk library is basically a way of centralizing this. So you'd set it up on an SQL server, and you'd have an oil price guru who sets the oil price across the organization, and then everyone uses the same input distribution for their models, so that you're comparing apples and apples rather than apples and oranges when you're looking at different, maybe evaluation models or whatever it is. So at-risk library, really, really useful if you've got lots of people across an organization working on the same, working on models with the same inputs. Okay. Project integration. I might run a couple of minutes over here, so I'm sorry about this. As I said, this bit's all been a little bit quick at the end because I obviously talked too much with my new opening at the start. But if there's anything that hasn't been covered, or you want it covered in more detail, as I said, please send me an email, explain what you want to know more about, and either I'll answer it if you're from the territory I look after, or one of my colleagues will instead. Example spreadsheets. I'm going to talk about at risk and project. I've got some. Okay, whereabouts are we? Okay. In the past, we have always had two versions of at-risk. One version was for Microsoft Excel. One version was for Microsoft Project. So with the project version, you kind of used to input distributions around task durations, costs, etc., and simulate. But of course, Microsoft Project is not really a particularly good tool for running simulations. It's really a scheduling engine with a database attached, and so doing any kind of like modeling is very, very difficult in Microsoft Project. And so what we've done with At-Risk 6, which was released a few years ago, or a couple of years ago now, is to integrate those two versions. And so here what we've got is a Microsoft Project schedule. This is called a Gantt chart for those of you who aren't familiar with it. We've got a number of different tasks, each of which has got different durations, start-finish dates, and different costs, etc. underlying. And this kind of shows that the project time frame, if you like, where tasks are dependent on previous tasks and so on. And so this is all in Microsoft Project. But what we've done with At-Risk 6 is we have added this extra button up here, which allows you to import a MPP file. And so instead of needing to build things in Microsoft Project, here is that same Microsoft Project schedule, which is now in At-Risk, or sorry, rather At-Risk is now imported into Excel. So this is the Gantt chart. These are our tasks. It's all exactly the same data, but this is now in Excel. And so what we can do with this, in exactly the same way as we've done with any of the other distribution or models that I've shown, is we can now assign uncertainty to our tasks. So here we've got distributions around how long a particular task is going to take. We've also got distributions around some of our costs and so on as well. And so if I put it on Monte Carlo mode, when I start pressing the F9 key, you can see that the values for our durations and costs are changing, and so then this Gantt chart here, which is in Excel, is being updated. And so what At-Risk has done, it's basically created a live dynamic link between Excel and Project. And so when I'm pressing F9, what the software is doing is it's basically taking samples from the distributions which we've put in. It's sending them back to Microsoft Project. Project is then recalculating the schedule, sending it back to Excel, and then it kind of updates on here. So I'm just running a simulation which is kind of going on in the background there at the moment. But that's kind of what this newer version of At-Risk is capable of doing. So really, really powerful. It allows you to take a project schedule, bring it into Excel, which is wonderful in the first place, with all of the dependencies and relationships, etc., and then to run a simulation around that. And so if I go to my finish date up here, so what that allows us to do, instead of having a deterministic finish date, obviously, I appreciate that this happened, that this is in the past. We should probably really update our models so that they actually happen in the future. But this is this was kind of this model was built at the time that the software was released. So here we've got a finish date of 2nd of the 2nd, 2012. Let's say let's imagine it's a bit later. But actually, what we've got here, we've now got a distribution of finish dates. So instead of having a fixed finish date for our schedule, we've now got a distribution of them. In exactly the same way as for our profit and loss in the last model. What we can also do with that, then, of course, we can build in uncertainties around our resource levels. We can build in correlations, so around task times or costs, etc. We can build in risk registers. So here we've got a risk register where we've got some different risks which could happen for some of our tasks, different probabilities. So here, just as before, we're using discrete distributions to simulate whether or not they're occurring. If they occur, they either add time to our schedule, or they add time, or they add cost. And so we're simulating different tasks, different risks occurring. They then get added into the project using some of these new At-Risk project add delay functions or add cost functions, and they get calculated into our model as well. So we've applied a risk register to our model. We can also pull out timescale data to look at kind of like the cost of a project over the whole time frame, which is really, really useful. And actually we can do some quite cool things with this as well, like look at the interplay between cost and schedule. And so if I go here, what I'm going to do, I'm going to add in the cost. And so now I'm plotting cost and schedule on the same graph. And so let's say, for the sake of argument, that our target finish date was the 18th of October 2012. Our project budget was 3.5 million. Okay, what we can see is that we've got a 34% chance of coming in on this project under time and within our budget. So some really useful things that we can do with that. And so I just used one of the example models. In At-Risk, under example spreadsheet, so help example spreadsheet, you've got lots and lots and lots, probably hundreds now of different example models for lots of different industries, for different applications and so on. So do take a look at these if you're kind of just starting out with the products. And on our website, here we've got, if I scroll up and go to support, under videos, we've got lots of different types of videos, quick start tutorials, and lots and lots of different things here. Okay, I'm 4 minutes over time. I haven't showed the time series side of things, so very, very, very quickly I will just show that. So before, earlier on I talked about, oops, what am I doing? Earlier on I talked about distribution fitting when you've got historic data, but actually sometimes that's not necessarily appropriate. You might have a time series that you want to look at and incorporate into your model. So whereabouts are we? I'll use the oil price one. This is just one of the example models in the software. So what we've got here, we've got some historical data which shows us the price of crude, gasoline and heating oil and propane between October 2005 and September 2011. So this is actual data. Here, if we go scroll up a bit, this was kind of the peak of the financial crisis, or the start of the financial crisis, where oil kind of peaked at $147 a barrel. So these are the average monthly prices. And so what we're going to do here, what we're going to use that risk to do, is to basically try and capture or describe these time series so that we can then use them as an input for a model. So what I'm going to do, I'm just going to go to time series and then batch fit, and in at risk, what we now have, we've now got a number of different time series processes: autoregressive, moving average, geometric Brownian motion, mean reversion, arc graphs, and so on. And what at risk is going to do, it's going to apply each of these time series processes to that historic data, and then it's going to tell us which is the most appropriate. And then from that, we're then going to use at risk to make some predictions about what happens next. So this data ended in September 2011. We're now in June 2014. So what does that kind of mean? That means maybe 33. We're 33 months after September 2011, I think. I may be 1 or 2 out. And so what we're going to do, we're going to use at risk to fit these time series processes, and then using the processes that it's fit to then make some predictions about what happens next. And 33 months down the line, hopefully, we're going to see what the prediction is for June 2014. And I'll put them in the same thing here. So if I scroll down, click on OK. Okay, so if I just delete these out, I'm just going to tidy this up very, very quickly. I apologise for going over my allotted 90 minutes. Hopefully most people are still able to stick around. Okay, so what we've now got, in each of these cells, we've now got a prediction for what happens next. So just the same way as before, what we're now seeing is at risk making some predictions about the price of oil, gas, propane and heating oil, whatever, going forward. And so if I just look at one of these, so this is crude. So this is crude oil. That blue line is the historic data. And then this red line is one possible scenario for what happens next. And so when I was pressing F9, I was animating it, or I'm going to animate it rather, and now you can see there's lots and lots of different predictions being made. And then here you've got your confidence envelopes as well. And so what we're doing, we're basically using at risk to find out what the most appropriate time series process is for the historic data, and then we're using it to generate some values for the future. and so I'm glad to see that my maths kind of worked out okay, and that actually we have got a prediction for June 2014. And so the way in which, or a way in which you could use this, was that if you imagine that you were standing back in September 2011 and you were building some kind of a financial model and one of the inputs to that model was that you needed to know what the price of oil was going to be in June 2014. And so what you could do is use something like a risk percentile function, which is one of the very cool functions in at risk, and say, okay, so what I want to do is I want to find out what the 95th percentile, so I want to be 95% confident what the price of oil is going to be in 2014. So now if I run a simulation, okay, so my P95 price of oil in 2014, based on that historic data, I'm looking to predict it's going to be 112. You know, the P95 is 112. As always, I can't remember exactly what the price of oil is. It's somewhere between $105, $110 a barrel, I think. So, you know, we're 95% confident it's not going to exceed $112 a barrel. If we're, you know, if we want to increase our confidence level, then to say our P99, we'd use, you know, we'd say $125 a barrel would be our P99. If we were kind of needed a lower confidence level, well, you know, we're 80% confident it's going to be less than 94.81 or whatever. So, yeah, that's the time series side of things. And what's really cool about this is that when we looked at that historic data, what that risk did, it also generated a correlation matrix as well down here to show the relationship between each of those kind of variables historically, and then it's applied that same correlation matrix to this new data here as well, so it's all kind of logically consistent. So I think that that's pretty much all, well, certainly all I've got time for. My voice is about to go, and I've also got another meeting scheduled in 15 minutes that I kind of need to do a little bit of prep for as well. There's a few kind of questions outstanding here. I think what I'm going to do, I'm going to apologise, but if you have got any questions that have not been answered, send me an email to doldfield@palisade.com, the email address that I sent before, and I'll either answer them myself, or as I said, I'll get one of my colleagues who's responsible for your particular area to answer them for you. I'd like to thank you all very much for your time. I hope that you found today's session interesting and enjoyable and not too dull or anything like that. And you know, obviously, any questions, please give us a shout. As I said, I've recorded this, so I'll send the recording link round to everyone who's signed up. So once again, thank you all very much for your time today. Bye bye.